Okay, now we move to the channel. That was another block in the simplified communication system that we introduced. Sorry, guys. This is one of the key important blocks in the communication systems, the wireless propagation channel. And the challenges of this channel propagation is very important, and it's one of the topic that is studied extensively in the literature. So we prepared, we processed, and we are ready to transmit our signal over the air using the antenna. So antenna basically it converts your electrical signals into the electromagnetic wave, and it radiates over the air. So once we radiate over the air, these electromagnetic waves or signal, it undergoes to the many effects, because if you're at indoor environment, it can hit to the right, to the walls, to the tables, the chairs, and whatever obstacle and objects that you have in this environment. In the outdoor case, it can, hit to the buildings, the trees, the mountains, the hills, and cars, even the peoples, and so on. So after each this hits by the objects, it can change the parameters of your signal, such as the phase, the magnitude, or the delay, or the time delay of your signal. So what are these channel impairments that we can talk, are given as follows. The first one is called distance dependent path loss. So this is your transmitter, this is your receiver, and there is a distance, right, between the transmitter and receiver. So you're talking your mother at Adana, you're in Istanbul, and your father and mother is at Adana. So it's about 1,000 kilometers, right? As the signal propagates from Istanbul to Adana, because of this distance, according to the physics law, the strength of your signal is going to degrade, and we're going to experience some path loss, in terms of the signal attenuation, and this is called path loss. And another effect is called reflection, scattering, or diffraction. So once we propagate or radiate the signal over the antenna, and it can reflect, it can scatter, or it can diffract, even it can refract, which is another type of physical phenomenon. And there's another effect which is called log normal fading, also known as large scale fading. Another type is called Rayleigh fading, also known as small scale fading or multi-path fading. And we have this multi-path delay spread, interference from other users, and so on. So there are many different effects when your signal undergoes to the channel. Let's start these effects and explain one by one. And the first one, as I said, we have a transmitter here, which can be a base station. And we have the mobile device, which is carried by a person in a car. The car is mobile, of course, or can be fixed. So, and this mobile device is connected to this base station. So the base station is transmitting some signal, and this signal can go through different paths. We call this as a path. This is the first path that goes to the hit to the building and it reflects. So each of these different phenomena has some condition. It depends on the signal wavelength compared to the size of the objects, which is in this case a building. So if it satisfies the reflection condition, it reflects the signal. Another phenomenon is called diffraction. So this one has some condition also. And this signal, it diffract, it changed the ways. Another phenomenon, the third path can go through this and it can scatter the signal. As you see, the signal is scattered. It's split into the multiple parts and only one of the part can goes to the mobile device. So as you see, there are different physical phenomena that affect my signal when it goes through the channel. So the first effect is called fading. So fading means your signal strength is getting down. So there we classify this fading into two parts. The first part is called large scale fading. So this is the loss due to the propagation models that we explain. It mostly depends on the distance between the transmitter and receiver. And this fading is called also large scale path loss or low normal fading or shadowing. The second type of fading is called small scale fading. And this small scale fading effect can be between 20 up to 30 dB. And this is caused by the superposition or cancellation of multipath propagation signals. You know, the movement, the speed of the transmitter or receiver, and the bandwidth of the transmitted signal. So this is also known as multipath fading, relay fading, or simply as a fading. So remember from this picture, when the base station transmit signal, it can split into the multipath. We call this multipath. The first path, path 2, path 3. And each of them can have a different attenuation, different delays, and different phase. So the copy of the same signal, it goes through these different paths and it cannot arrive to the receiver mobile devices with different delays. And these paths can constructively add them up or destructively they can cancel each other, which is gonna lead to the fading. So let's start with the path loss, which was a large scale fading. As you see, this is my transmitter, 0 meter, and this is my receiver. As you increase the distance between transmitter and receiver, as you see, the signal strength decreases. So as the signal, move forward from transmitter to the receiver, the strength of the signal also decrease. And we model these effects, and it's really different and very complicated to model these effects because each environment can have a different path loss. A simple model for path loss L is equal to average received signal over the transmit signal, and which is equal to k times 1 over distance to the power of alpha. D is the distance between the transmitter and receiver. K is a constant that consists of many effects such as the transmit antenna gain, receive antenna gain, and so on. So distance over power of alpha. Alpha in this case is called path loss exponent, and it can be between 2 to value of 4. When the alpha is equal to 2 is equal to the free space, which is the idealistic case. And for each different environment, we may have a different path loss exponent. For instance, in this classroom, alpha can be 2.3, and the outdoor can be, for instance, 3.7, for instance. So each environment can have different path loss exponent, and it's really complicated to estimate these path loss exponents. So as you see from the picture, if you increase the distance, your signal strength decreases, right? Which means that was your transmit signal, that was your receive signal. So if you increase the distance, the loss, path loss decreases. So the path loss increases, the received power decreases. There's another effect which we call shadowing. So when we radiate the signal over the antenna, the signal can hit to different obstructions, obstacle objects, right? Such as hills and buildings. So the effects of these buildings, trees, mountains, hills is called shadowing. So once your signal hits to this obstruct, it results into some signal variation in the local mean of the received signal power, and we model this shadowing effect as follows. Received signal power is equal to average received signal power plus the fluctuation, which is a shadowing effect, and denoted by GS. GS is modeled as a log normal distribution with zero mean and with the variance of sigma s squared. So this standard deviation, the effects of the shadowing can be between 4 to up to 10 dB. So what are the result of consequence of this shadowing effects is the non-uniform coverage. So if you have a non-uniform coverage, in some case you need to increase the required transmit power, and you need to even come up with some adaptive transmit power mechanism. Okay, let's show all these effects. Remember, there are three fundamental: path loss, shadowing, and Rayleigh fading. So the smallest scale one is called Rayleigh fading. This fluctuation by the red lines, red color. This is the real signal that we obtain, practical. And the average of this Rayleigh fading gives us the shadowing fading. And the average of that shadowing fading, green line, give us the path loss, which is the blue curve. So as the distance increases, you see the path loss, the received signal's power also decreases. So the speed is a mobile communication we are talking about. You can be in a car that moves like 100 kilometers per hour. So as you move forward, we experience some fading due to this movement. And this is a typical received signal that we obtain. As you see, it fluctuates. It has a lot of fluctuation, which we call Rayleigh fading. And we talk about the multi-path propagation. So between transmitter, in this case is the base station, and the receiver, which is a mobile device carried by a person in a car. So when the base station transmits some signal, it can go through different paths. So the shortest path is called line of sight, the shortest path, which arrive first, because this is the shortest path. Then we have another second path, third path, and fourth path, and so on. So each of them, because arrive at different delays, so we modeled this profile as a multi-path power delay profile. Each of these impulses represent a path which has a amplitude, phase, and a delay. So let's consider two-ray model to show you guys the delay, RMS delay spread. That is the bit 1 and another second bit that I'm transmitting. Because of the channel effects, we experience a delay spread. So in this case, tau is the RMS delay spread, and t is our symbol duration. If t over tau, if tau over t is small, that means the intersymbol interference is negligible. So we have a, depends on the amount of the delay spread. The channel can shift your symbol to the on top of the next adjacent symbol. So we have a bit 1, bit 0. Remember, bit 1 in this case. Because of the channel effects, in this case, the delay spread. So you may experience intersymbol interference. So the first symbol or the bits can move to the next symbol or bits. So at the receiver side, it's gonna create some problems because they're gonna mix to each other. These bits can overlap each other, and then it's gonna create a problem when I decode, reconstruct these bits. So that's why the channel delay spread is important when you design a communication system. If the tau over t is large, then we have a significant intersymbol interference in the green case. So this symbol, this number of group of bits overlap with the next group of bits, which is going to mix to each other and even may, cause some error. So intersymbol ISI, intersymbol interference, is one of the fundamental problem in the communication system that we need to address. Okay, another important effect is Doppler effects, which we measure by the Doppler shift. How this Doppler happen? The channel varies with the user location, mobile user location and time, if it's moving. So especially when it moves. So this movement or the location and time change results in a rapid fluctuation in the signal strength. So it creates some, fluctuation in your signal strength. As I mentioned, the moving user introduces Doppler shift, and Doppler shift can increase the signal bandwidth. So because of this movement, it creates a Doppler. Doppler can increase your signal bandwidth. So what is the amount that is increased because of the Doppler shift? So we calculate based on the following equation. This is the equation for the Doppler shift, which is equal to the speed v over the signal wavelength, which is lambda. Let's give an example. My frequency carrier is 900 megahertz, which is typically a GSM frequency carrier. And assume that you have a mobile device that is moving with the speed of within a car, which is 60 miles per hour, which is equivalent about 100 kilometers per hour. In this case, if you calculate the Doppler shift based on this equation, and you end up with the 80 hertz. Okay, guys, I was dropped. Are you there?
Yes, sir.
Yes, sir.
Okay, let's continue. I was talking about this Doppler shift, right?
Right, sir.
Because this moving mobile device, it introduces Doppler shift, and Doppler shift can affect your signal bandwidth. It introduces some fluctuation. How do we measure this or calculate this Doppler shift? It using this equation. So first of all, there are two examples. The first one is for GSM technology, where we use around 900 megahertz frequency carrier, and assume that the car is moving with the 60 mile per hour, which is equivalent to the 100 kilometers per hour approximately. If you plug in this value into this equation, and you end up with the Doppler shift, which is equal to 80 hertz. That means your signal bandwidth is going to fluctuate by 80 hertz due to the Doppler shift. And second example is for the Wi-Fi, which operates at 5 gigahertz bandwidth, and is relatively with the lower speed, because mostly is a laptop, within an indoor environment. If you convert into the kilometer per hour, it's approximately 8 to 9 kilometer per hour, which is like a walking or running speed. And if you plug in this value to the same equation, the calculated Doppler shift is equal to 37 hertz. As you see, so the speed in this case is more dominant. So we have some function that we model the channel that we talk about, this reflection, scattering, diffraction, all they end up with some function, channel function. So Fourier transform of this correlation function relative to t, and this scattering function is different for each environment, and we model as a white sand stationary and Gaussian channel. So the autocorrelation function of this is given by AC tau t, and if you apply the Fourier transform this to autocorrelation, you obtain the scattering function of a wireless channel. So we have multipath intensity profile in order to determine the average delay spread or RMS delay spread, average maximum delay spread or RMS delay spread of the channel. Once you obtain this maximum delay spread Tm, if you take the inverse of this, you obtain the coherence bandwidth of the channel. What is the coherence bandwidth of channel? Is the bandwidth, is the frequency bandwidth that channel is not changing, is fixed. So that's what we call coherence bandwidth, and it's obtained by 1 over Tm, and Tm was maximum delay spread. Another one is the Doppler power spectrum. Doppler spread BD is the maximum Doppler for this spectrum, and we utilize this Doppler spread in order to obtain the coherence time of channel. So coherence time is the channel where the channel is not fluctuating, is fixed. So that's all for the wireless channel and for today's lecture. Any question? Guys, any question? All right. That's all for today.
Sir,
Yes.
can you share the slides? Today?
Slides?
Today's slides, can you share?
Oh, you have a question?
No. I'm just say, can you share these slides?
Put on the MS Teams? Do you want to put this on the MS Teams? Who was asking the question? I guess there's no question. All right, guys, thank you, and I'll see you next week.